Okay, so we're back with the first few videos just regarding antiderivatives. So we had some rules for derivatives. Let's have some rules for antiderivatives. So first of all, just notation-wise, we see our integral symbol right here again, but yet there's no numbers. If you put numbers, a and b right there, what we have is known as the definite integral, okay? If there are no numbers where we usually see a and b, now it's called an indefinite integral. So you might hear me say that term. You can also just hear me say antiderivative. If we just see the integral symbol without the values, it's known as the antiderivative, okay? So let's take some antiderivatives. So the first one we just did in the previous video. Let's say that we just have a constant k. All right, this is 5, this is 12, this is pi, this is whatever, okay? What's the antiderivative of a constant? All right, based off of the previous video, we know that all we're going to do is we're just going to have k times x, okay? Because the derivative of kx, the derivative of 5x, would be 5. The derivative of 12x would be 12. The derivative of the opposite of x would be -1. So no matter what we have here, for our constant, if we just chuck an x after it, then we have an antiderivative. Some of you are probably thinking, wait a minute though, let's say that f of x is 4x. Well, then the derivative of that would be 4. And that's absolutely true. But you're also thinking, well, wait a minute, and if you're not, let me pose this question to you. What about the derivative of 4x plus 1? What's the derivative of 4x plus 1? Exactly. It's also 4. All right, and in fact, the derivative of 4x plus anything will be 4. 4x plus 12 will be 4. 4x minus a million has a derivative of 4. So this value right here, we need to take that into account because it could be 1, it could be pi, it could be -1,000, it could be 0, like this. This is 4x plus 0 technically, correct? All right, and no matter what, we have this constant at the end that we have to take into account. This constant could be any number. It's arbitrary. So what we have is we have an arbitrary constant. What that means basically is when we go back to our antiderivative, we need to put this arbitrary constant into play, and that's plus c. All right, and this plus c is basically saying, hey, you know what? Because when you derive a constant, you get 0. When you antiderive, we need to take this into account because it might actually be there. Now, c might be 0, in which case the antiderivative will just be k times x. But it might not be. But whether it is or isn't, we just need to write the notification that it could be there. So this is our arbitrary constant. Whenever you do an antiderivative, you must remember to have the plus c there. Okay, and there's our antiderivative of k. Kx plus the arbitrary constant, kx plus c. Let's do another one. We have the antiderivative of x to the nth power dx. Okay, so this is kind of like our power rule, if you will. Because remember, if we had the derivative of x to the 5th, what's the derivative of x to the 5th? Yeah, you're all thinking 5x to the 4th, okay? Because you would take the exponent and move it down out front, and then you would subtract 1 from the exponent. Well, now we want to go in reverse. Okay, so if we think about what happened when we did the power rule, we subtracted 1 from the exponent when we were deriving. But if we're anti-deriving, instead of subtracting 1 from the exponent, what should we do? Exactly, we want to add 1 to the exponent. All right, so we're going to have x to the n plus 1 for starters. Okay, now we also have to take into account what happened to the old exponent. Remember, x to the 5th went to 5x to the 4th. So we multiplied the derivative by the old exponent. Okay, the opposite, and we're doing the opposite of that now. Okay, so instead of multiplying the derivative by the old exponent, we're going to divide the antiderivative by the new exponent. All right, and that is going to wipe out our, in essence, the coefficient there. So let's think about this as, well, before we go anywhere, let's put plus c. Okay, so we have to have that in account. Let's actually do an example that'll make things a little bit clearer for you. Let's say that we have, it's example 2, we have the antiderivative of x squared dx. Okay, we want to do the antiderivative. So we know that if we were doing the antiderivative, we're going to add 1 to the exponent. So that means that we're going to make it x to the third. Okay? Now, if we just took the derivative of x to the third, what would our answer be? Yeah, it would be 3x squared. But we don't want 3x squared. We want x squared as our, as to be our derivative. So what that basically means is we're going to divide by 3. All right? Because if we have the derivative of x cubed, that's 3x squared. And then the 3 out front will get eliminated by this 3 right here, were we to actually derive our answer. And that's the key thing. Whenever we do antiderivatives, you can always check your work. You just need to derive your answer. All right, so we have x cubed over 3 plus c. That is the antiderivative of x squared. And again, I know this because if I derive my answer, I'm going to get x squared. Let me go right over here where I have a little bit of space. All right, f of x is 1/3 x cubed plus c. I want the derivative of that, so I know that 1/3 will move down into the answer. X cubed has a derivative of 3x squared. And the derivative of a constant is always 0, and the 1/3 and the 3 wipe each other out, leaving me just with x squared. So this, in fact, works out to be true. That's our, if you will, the power rule. Now, there's one more caveat that we have to talk about with this. We're dividing by n plus 1. What's the one thing we're not allowed to do in math? Exactly, we cannot divide by 0. Okay? And if n is -1, well, -1 plus 1 obviously means we'd be dividing by 0. So this rule works as long as n is not -1. We'll talk about that more in the next video.